Buffering here. Second for the buffers. Okay, there we go. All right. So I want to make a claim, and I want to make you believe in this claim. So an assertion, if you will. This is that claim. In 2D or 3D motion, I'll explain what this means in a second. Okay, so this is that claim, and you don't need to write this down. I'm just putting it down, and I'm going to try and make you feel comfortable with this claim. In 2D or 3D motion, the X and Y motion equations can be treated independently. So basically, my claim is this. You could do an X of time equation. You could do a Y versus time equation. And you could even have a Z versus time equation. Sorry if the green's not showing up, but whatever. It's pretty faint. I'm going to try and do it in a different color here. That's probably a little better. Wish I could get a nice dark green, but whatever. The idea here is, this is my claim. I think if you could figure out an equation of motion for the X equation, it will have no effect on the Y equation and the Z equation. And similarly, Y should have no effect on there. In particular, we should be able to write, as an example, if acceleration equals a constant, I should be able to write delta x, v initial x, v final x, a sub x, and t. And these variables should have no effect on delta y, v initial y, v final y, a sub y, etc. So basically, my claim is that these parameters should have no effect on these parameters. So far, so good? Let's try and prove that. All right. Oops, I want to go to 4, and then I zoom out. I want to move this way. Oops, wrong way. Okay. So right now, I'm looking at this device right here. Alan, am I still showing up? Yeah. Okay. Now I've got 2 metal spheres here. Right up my sleeve. And the idea is if I put them on this weird contraption and I push this lever, it will make both of them release at the same time, almost exactly. And so the idea is I can put one here and one here. One of them is going to drop straight down. The other will be launched horizontally across the room and hopefully not hit too many students. All right. Super delicate. So now I know you can't all see the ground, but if we're very quiet and listen for the number of impacts. Now they're going to bounce, and after the first impact, you might hear multiple bounces. But my claim is, right, this one that's launched horizontally, the horizontal motion should not affect the motion up and down. If that's true, we should hear a single bounce at the first impact. So let's listen. Ready? Here's just one bounce initially. Now, obviously, after that, we heard multiple. So this is one example showing that launching this thing horizontally has no effect on the time it takes to hit the ground. Now, obviously, if you launch it upwards, that would be different because there would be some vertical component. All right. Here's another example. Let's go to page 71 in the workbook. Go to page 71 in the workbook. Actually, we'll just get this next in and wind up.
You launched it.
Yeah, yeah. Did you see it? Did you get it? Oh, yeah.
Keep it up.
Oh, yeah, here, just do it. All right, got it. Thanks. I probably would have forgot that. Thank you. All right. So now, what did I say? Page 71? Let me get there myself. 71, 71. Make sure that's the right page. Okay. Hopefully on your workbook, you see something that looks like what I've got right in front of me here. Okay. Oh, geez. Have I been running this all day? Yeah. Okay. Let me show you something here. Get a marker. Okay. Take a look at this weird device. There's a little spring inside of here. Okay. There's a little spring inside of here. And I can put a ball in there. There's this weird little contraption right here called a photo gate. Now, you'll notice there's a small piece of paper right here where I'm pointing. In this case, if that piece of paper slides through here, let's see what happens. I'm going to try and do it very slowly. Okay, here it comes. Did you see that when this thing is, when the beam is broken, it launches the ball straight up, right? So now, the questions I have for you on page 71, look at questions 4.1, 4.2, and 4.3. I'm going to try and write those questions up here on the board really quick while you take a look at them. Discuss with your neighbor the following idea. Where's the ball going to land? If I push it and it's moving with approximately constant speed and it breaks the beam, will the ball land in front, behind, or back in the cart? If I tie a little string to it and hang a mass, will it land in front, behind? Or if I angle the ring? Go ahead and discuss with your neighbors as much as you want, all right? I'll write them up here.
Yeah, something like that. Like that, something that affects the acceleration of the dimensions.
More and then we'll do it. So as soon as I get these written up, we'll discuss. Talk with your neighbor as much as you want.
Yeah, I think so.
All right, ready? Let's take our vote and then we'll run it, okay? So in this first case, the cart is gonna be moving, let me see if I can move this just a hair up, sorry. There we go. Sorry about that. In problem 4.1, the cart's gonna be moving with constant speed, okay? And then it's gonna hit the launcher and it's gonna launch. Just go ahead and vote. It's okay. Just be interactive. The science about learning says if you take your guess, you're more likely to remember the correct answer, even if you guess wrong. And so let's just try it. How many people think the ball will land behind the cart? Just take a guess. Okay. Maybe we got 1, 2, maybe 1, something like that. How many think it's going to land back in the cart? It looks like most. Okay. How about in front? Okay. All right. Let's try it out here. All right. And then do you want to do me a favor? Can you just stand at this end and basically make sure it doesn't smash? You know what I'm saying? And I don't think you're going to show up on Zoom if you just stay at the end there.
I'm not blocking the camera.
You are blocking the camera. Thank you for reminding me. You want to scoot over? Sorry, I should have made him do it, but yeah. No, you're good. You're good. You aren't even showing up on camera, so don't worry. Okay, ready? Okay, here we go. 1, 2, 3. Back in the cart. Okay, sounds good. All right. Now, just give me a second. Let's take the next vote. For this scenario, 4 point. Let's give a round of applause, everybody. In this case, there's a hanging mass. Right. Oh, and let me mention this, right? The idea here is the initial velocity horizontally should have no effect on this, or the upwards motion should have no effect on the ball's horizontal velocity. Remember, when the ball is launched out of here, it has initial velocity horizontal as well as vertical because it's moving with the cart. And the whole point of this was to show that the motion up and down is independent of the motion left-right. So now let's go to this one. In this case, when the ball launches, how many think it will land behind the cart? 1, 2, 3, 4, 5, 6, 6.5, 7. How many think it will land back in the cart? A couple, like about 5. How many think it's going to land in front of it? Okay, no one. All right, so now let's do this. What I'd like you to do. Basically, can you hold this string right here, just right there? Got it? Yeah. And now to do this, okay, now I got it. You can let go. Okay. And now I need to, because this one's going to be accelerating, tell me when that should, whoops, is it? Oh. Thank you. Okay. Now I need to move this over here just because the cart is going to be accelerating this time horizontally, right? Yes, question. Oh, that would also be good. Thanks. Thanks, you saved me a trial there. Okay, so in this case, are we ready? And then if you could try and catch it. This time it's going to be moving a little faster, so don't get your hand smashed. Ready? Okay, here we go. 1, 2, 3. Lands behind. All right, that's good. I can get the rest now. Let's give a round of applause again. So now comes the fun one, right? So this is, hopefully this makes sense. When this ball launches out of here, it's got a velocity x and a velocity y. But once it's launched, it's not accelerating horizontally, whereas the cart is going to have an acceleration in the x direction that the ball doesn't have. And so in this case, the cart has a different acceleration horizontally than the ball, and that's why the cart keeps speeding up, whereas the ball keeps that same initial value of its horizontal velocity at the second it was launched. So the cart speeds up and gets ahead of it. All right, so far so good. Now how about this one? In this case, how many think the ball will land behind? Nobody? Okay. How many think it will land in the cart? 1, 2, 3, 4. How many think it will land in front? Most. one of the fun things about teaching physics is very often most people are wrong. So in this case, let me do this. Okay. In this case, actually, you want to come catch the card for me? Sorry, I forgot I did that. Put that ball down. Okay, and I'll try and explain this once we do it. So just catch it when it gets down there. Ready? Pretty close to right back in. Do you agree? Now there's a little error. Let's run this one more time. Need a steeper angle here. See if it's just close because of the angle. All right. Now it's going to go a little bit faster. I'm going to scoot this up just a little bit more, just so we don't run out of track. I got to remember to push this in. There we go. Right back in here, right? So again, if there's a little bit of error here in terms of the ball shooting out of this cart, we can even try one more angle. Keep going up. All right, here we go. Oh, so there it went off left, but it was still right at the plane, right? So in this case, let's give him a round of applause here. All right, so why is this doing this? Why does it go right back in there? Seems kind of counterintuitive. Wrong way. Let me do it like this. Here's what I like to think about. Imagine if we draw a coordinate system like this. Now, the coordinate system itself shouldn't affect the motion of the ball. It's just how we interpret it. But when you think about it like this, gravity points which way? Straight down, right? And the idea here is, give me a sec. There's an AX, oops, an A subscript X for the horizontal and an A subscript Y. Now, the whole point in doing this is to show you that the X and Y motions are independent. Now, think about this. When the ball launches, gravity acts on the ball. Both components, AX and AY, agreed? Now, when the cart is moving down the ramp is able to balance the forces perpendicular to the plane. So for the cart, there's no AY, but it still has the same AX. So in this case, when we view it under that coordinate system, the cart and the ball will have the same components of acceleration down the plane. They have different components of plane, different components of acceleration perpendicular to the plane. But because the X and Y motion is independent, it doesn't matter if they have the same AY. As long as they have the same AX, the ball still goes back in the cart. What do you think? So far, so good? What was the point of this? Let's go back to the first board. I hope that was worth doing. The whole point was this. My claim or assertion is that we could treat the X equations and Y equations separately. What I was trying to point out is a few different examples where this was valid. Even this crazy example of the ball going down the ramp, right? It actually works out. So this is true. We can treat the X motion and the Y motion independently. In particular, this is useful because if acceleration is a constant, we could treat the X motion like the speeder and the Y motion like the cop from last time. Remember when we did two-stage problems, there was a cop and a speeder? We could use the cop equations and the cop variables, and then we use the speeder equations and the speeder variables, and they had the same T. That's still going to apply here, because when you throw an object, oh, that was pretty cool. When I throw this object across here, it's in flight horizontally for the same amount of time as it is vertically, right? It's in the air moving horizontally for the same amount of time it's in the air moving vertically. And so we're going to, it's almost identical to COP, where there was no acceleration in the X because there's no gravity in the X. And the speeder, which had an acceleration. Or wait, which one was it? Whatever. The one of them had no acceleration, and that was the X coordinate. And one of them did have an acceleration. That's going to be like our Y coordinate when we're throwing projectiles around. Sorry if I misspoke there. So far, so good? All right. So the classic thing we want to start with is on the next page, 72. We're going to talk about projectiles. And I know almost everybody does this in every single high school physics class or in every single 110 class, so you probably know a lot of this. I need a second to erase the board. You can skim over this page 72 while I'm erasing. So I'm going to erase both boards real quick. All right. And if you want, you can talk to your neighbor as much as you want while I'm erasing. Do whatever you gotta do. Thanks, Alan. All right. Whiteboard. Okay. All right. So I'm going to draw a picture really quick. I'm going to imagine us kicking a ball or something off the top of the building. Do this. Okay. Hopefully that's showing up. Can you guys see that in the back? No? Okay. So imagine you kick a ball off the top of a building. This ball is going to fly, and gravity is going to pull it down below its straight line path. And somewhere over here, we would expect it to hit the ground. Now, I'll explain what I mean by impact in just a minute. All right. It's going to hit, and there's probably some weird angle right here. Okay. So a couple of things here. Notice I've used the word speed, not velocity. Together, the initial speed and the launch angle, that's a magnitude and a direction. Together, the speed and angle give you the initial velocity. Is that okay? Similarly, the impact speed plus the impact angle gives you final velocity or impact velocity. A couple of things here. I know this seems silly, but when you are working, it's crucial that this is theta. This is some other angle. They might not be the same, and in general, they rarely are the same. So when you're drawing your thetas, that's a perfectly horizontal line. When you're drawing your phis, it's a nearly vertical line, right? So when you're drawing your symbols, it's crucial that you draw thetas distinct from phis. I know that seems silly to mention, but I've seen it where students get kind of lazy and then halfway through the problem, you can't read. There's going to be a lot of problems where we have both theta and phi in the same problem. You have to get used to drawing them neatly. Okay, another thing. A very common question when people are starting these problems. Oh, is there a chat question there? Or is that's probably you, Alan, right?
Yeah.
Right on. Thanks, Alan. Yeah, definitely. Zoomers, you could definitely speak up or tell Alan to speak up on your behalf. All right. Now look at this. When I have this marker here, and let me do this. Okay. When I have this marker and it drops and it stops right here. Sorry about that. One more time. Okay, whatever. Slow motion. Yeah, it stops. This gets kind of confusing. Impact, oftentimes students say, well, is impact just before it hits the ground? Is it just after? Is it while it's hitting the ground? Good question. For a projectile problem, we assume impact is actually instant just before object hits ground. So one of the things you might be saying, like, isn't the impact velocity 0 because after it impacts, it stops? You're right in that it stops, but for a physicist doing projectile problems, for us, impact speed, notice how I didn't even draw it touching the ground. It's like 1 nanometer above the ground, just before it hits the ground. So emphasizing that just before. When I talk about impact, we're talking about just before. Everybody good with that? Okay. Now, this is what I would call a standard projectile problem. In a standard projectile problem, right? Just after launch, just after the kick, throw, or launch, just after you kick, throw, or launch this ball, what forces act on the ball? What do you think? Gravity's one. As a ball flies through the air, what else might act on it? Air resistance. If you recall from a couple of lectures ago, including air resistance is very difficult. We're going to assume air resistance is negligible. If you needed to incorporate air resistance, negligible, we could always code the problem, and I could show you how to do that later. If air resistance is negligible, gravity is the only force. We gave that type of problem a special name. What was it? Free fall. So sometimes if you're searching the internet, these might be under free fall problems. Okay. And again, this is an approximation we are making. Which way does gravity act? Straight down. How much does gravity pull you left or right? Right now. It's very close to 0. Now think about this. Do you agree like the sun could exert a horizontal gravitational force on the earth? Now, technically, I am attracting all of you with gravity right now. It's so weak the force is like 10 to the minus 11 newtons. It's so small, we could completely ignore that force. So for all intents and purposes, let's assume gravity acts straight down, all right? So if that's the case, the acceleration due to gravity should also point straight down, right? So there's gravity that's pointing straight down, which causes an acceleration due to gravity. So this is not gravity, right? G is 9.8 meters per second squared. It's the magnitude of the acceleration due to gravity near the Earth's surface. So far, so good? Trying to be thorough here. Okay. Generally speaking, unless there's some really good reason to do it, and occasionally there is, we're going to put our coordinate system right here. We're going to call this the x direction and this the y direction, right? Unless you have some reason to do it, like if you throw a ball downwards, maybe you would flip the coordinate system upside down. Unless otherwise specified, this is our coordinate system. You don't have to use it, but if you choose to not use this, you better warn me on your paper when you're doing your test so I can understand your work. Based off what you see right there, what is AX and what is AY? How much of the acceleration is horizontal? How much of it is in the Y direction? It's G, and then what direction? Yeah, opposite the coordinate, in this case, downwards is negative. Is everybody cool with that? So when we're making our lists of knowns and unknowns, we're going to have a list of X unknowns and a list of Y unknowns. In this case, A sub X should be 0, A sub Y is negative G. All right, take a look right here. There's a component pointing horizontally. I'm going to call that V initial X. I want you to really pay attention to the subscripts when I'm talking right now. Notice the initial speed is the magnitude of this vector. That's V initial with no other subscripts, right? This is not V initial X. It's not V initial Y. It's V initial. This is the initial speed. V initial X in this case would relate using SOHCAHTOA. So in this case, because it's adjacent, I can tell I'm going to end up with a cosine theta right here. Notice the subscripts. V initial X is related to V initial using the angle. What you don't want to do is say V initial X equals V initial X cosine theta. That doesn't make any sense. So my pet peeve is when people write a V initial X and then a cosine theta on top of it. That's like double counting the cosine. That's wrong. So the X component is the initial speed times the angle cosine. All right, so far so good? This side should be V initial Y, and there's going to be a sine theta. Do you agree? Because it's opposite. So far, so good? And I think, again, just reminding you, most of these notes are on page 72. So if you're looking, you could be looking at page 72, and then you just, if you see something that you want to add to those notes, you can just write it on there. Okay. Get out of the way just a second. What would be a good name for this component right here?
Sine phi.
VF sine phi, not theta. And it's how does that relate? What's another way that we would probably write that? V final Y. So far, so good. Similarly, this would be V final X equals V final cosine of phi. So far, so good. almost always, this is a special thing you got to watch out for here. Notice, usually, objects are going to impact moving downwards. So we're going to have one of those issues when we're doing problems. You may need to think carefully about minus signs with the final velocities. Very oftentimes, we expect a negative number for here. So then notice in this picture, right, we might expect a negative associated with this. So maybe I'll put in a little comment here. Think about plus minus signs, right? And technically, we should be doing that for any of these terms. For example, over here, if theta was a negative angle, you'd be throwing it downwards. We might expect that the initial y could be positive or negative as well if you throw something downwards, right? So I'll just put think about plus minus all the time. Those are the two main ones where it appears. Okay, question for you. If you had to guess, based off this problem and the way you see this sketch, which term do you think will be bigger? V initial x or V final x? Which one do you think is going to be bigger in this case? It's thrown sideways at an angle and then it goes downwards. What should happen to the speed of it? Oh, go ahead.
The final would be bigger
What's your reasoning?
because it's from a high spot, so
Okay,
it'll accelerate.
it's a great idea. Turns out it's not right. It's the same. Check this out. Do you agree the vertical motion doesn't affect the horizontal, right? That's what we're trying. Do you agree that we said there's no acceleration horizontally? So that means this shouldn't change. It should be, do you remember when I was doing this, kind of like eyeballing it? I was trying to remember because I know that the final velocity in the x should actually match the initial velocity in the x. Sorry if it's not perfect. But again, it's from this independence of xy motion. That's the piece that gives us that puzzle. Clearly, it's speeding up in the y direction. It also reverse direction. But the y direction has nothing to do with the x. Good? Sneaky, sneaky. All right. Let me see what else I want to say. How about this? What's a good name for the shape here? What do we call this path that the object travels? What's a good name for that? Yes, that's a mathematical description of this shape. That's true. So it's a parabolic path. Let me rephrase. What is the name for this special kind of parabolic path? Starts with a T. The path that an object travels through space is sometimes known as its trajectory. Sorry if I didn't make that clear. And green doesn't show up, does it? This path is called the trajectory. Right? The path that the ball takes through the air is the trajectory. So far, so good? I'm going to look at my notes and see if I'm what I wanted to say next. Oh, here's something. When you throw a marker like this, take a look. Ready? Watch the marker carefully. In particular, watch it at max height. Ready? Hit max height somewhere over here. Is it moving at max height? Or is the velocity 0 at max height? What do you think? Discuss with your neighbor. Will I collect all these freaking markers? Okay. When it reaches maximum height, is the velocity 0 or non-zero? What's your gut tell you? Speak up. It'll make you more interested in the answer. What do
I
you
would
think?
say it's 0.
It's 0 in one component, but not 0 in both components. Which component goes to 0 at max height?
The y component.
So it's 0 in the j hat, but it's v initial x in the I hat. Think about it.
The x component of velocity doesn't change. It's always
This much as it travels horizontally.
why? Because the x motion and the y motion are independent.
Okay, the vertical gravitational force has nothing to do with the x motion, and so it doesn't change as it moves across.
So
One of the more common mistakes is people will say velocity equals 0 at max height.
that's so close to correct. And that's true if you throw it straight up, but it's not true in general. The velocity final in the y direction is what's 0 at max height. Good with that? All right. So what about the acceleration at max height? Is that 0, non-zero, or what? What's that? As? Yes, I was trying to hide it. Hopefully I succeeded. The idea is, look, gravity's not turning off and on here, right? There's the same acceleration throughout the whole thing. So to be clear, acceleration max equals a equals a constant equals negative g in the j hat, 0 in the I hat. So don't overthink it. Now, to be clear, I want to warn you of something on me on test day. Almost always I ask some questions like this, either on the midterm or the final or both, the first midterm or the final or both. And I'll say, what is the acceleration at max height? And people will write negative g. Not true. A sub y is negative g, or so like, look, this is one way to state the acceleration clearly. You specify both components, or you say it's negative g in the j hat. But I'm just telling you right now, I will mark you down if you just write negative g, because technically that's not right. The acceleration is a vector, you got to include that unit vector. Everybody cool with that? Similarly, if I ask you about the max height velocity, you got to remember it's something in the I hat, nothing in the j hat. Just not trying to scare you, but I do it pretty much every year, and people miss it every year because they forget that I'm picky about that. Just warning you. Everybody cool with that? You'll see it on the practice test when you get there. All right, so that's max height. Somewhere right around in there. Okay.
Let me see what else I want to say.
Oh, to be clear here, I hope you agree that V final, and I'll get out of the way. You could get the final speed by using the Pythagorean theorem. Square this one and square that one, add them together in quadrature. And then notice when you're doing that step, fortunately, we don't have to think too much about the plus minuses. So a lot of times I will literally ask for the impact speed and angle on a test question. That way we don't have this confusion about should I include the plus or minus or not or what. So that's why I oftentimes ask for impact speed and impact angle instead of these components. This removes that difficulty. Similarly, how could I get phi? How does phi relate to these sides of the triangle? So, ka, or toa? Toa. So it should be tangent inverse of what over what? X over y or y over x? Y over x in this case. Now again, if you're worried about plus minus signs, which you should be, one of the ways I handle this is usually what I will tell you is
draw me a picture and show the final angle. That way we don't have to worry about plus minus signs. So a lot of times what I will do is I will take the absolute value of this and then just draw a picture. Okay? Some other teachers may want you to include the angle, and they might not include the absolute value sign. It just depends. So just, yeah, okay. So far, so good with that? That's just standard trig. All right. What else do we got? One more thing. Let's do this. Come on. There we go. Now, you could imagine we're going to write some equations that look like delta x, v initial x, v final x, a sub x, t. Then we're going to have delta y, v initial y, v final y, a sub y, and I'm not going to write the t. In this case, sorry that's so sloppy there. More like a delta now. Okay. In this case, I want to point out we're assuming, right, this thing is flying horizontally for the same time. So previously, when we were doing a 1D motion problem, we'd have 1, 2, 3, 4, 5 variables. Usually there were 3 things that were unknown, something like that. Or I mean, there were 3 things that were known and 2 things that were unknown, or something like that. Well, now we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 parameters. Okay, 11 if you were using this. If you did x final and x initial, right? That'd be 2 parameters instead of 1. You could also do y final and y initial. Sometimes some problems are easier like that. So you can imagine you're either going to have 9 or 11 parameters depending on how you write your equations. There's going to be a handful that are known, a couple that are 0, and then some stuff that's knowns and unknowns. All right. There's going to be an equation associated with each of these, right? You can have the delta x equation. You might say, are there other ones? We'll take a look. The delta x equation is v initial x times time plus 1/2 a sub x t squared. Remind me, in these types of standard projectile problems, what is ax? 0. When that's true, basically there's only one x equation worth discussing. This. It turns out, almost always, we can set x initial to 0. Notice if x initial is 0, we could rewrite this equation as x final equals v initial xt. And to be clear, what do I mean by setting x initial equal to 0? I'm talking about this. Look, all you do is you line up your coordinate system so that the origin is directly beneath the projectile or on top of it. Okay. So whenever you do that, x initial is going to be 0, and then delta x is the same thing as basically the x coordinate. Agreed? So sometimes I'll drop the subscript f as well. So a lot of times I'll just be like, screw this, it's just x. And that's probably how you did a lot of your homework, right? So that's why in almost all these problems, we use x, delta x, x final. We're going to use those all interchangeably. It's because we set x initial to 0, and there's no reason not to do that overwhelmingly if we can. Now check out this one though. Okay, I could rewrite this one. Let's go through this equation briefly. which of these terms are constants and which of these things are things that might be different? Well, if you're launching a ball, we might have the time to reach max height. We might have the time to hit the ground. Time is something that might be best considered as a variable. So I want you to think of t as being a variable. What about a sub y? Is that constant? For a standard projectile, is the acceleration in the y direction changing? Is gravity changing? No. Unless you launch it really high so that it goes up into outer space, gravity is the same value approximately all the time. So this is a constant. What about v initial y? Is that going to be changing as the ball flies around? That's the initial velocity, not the velocity. The velocity is changing all the time, the velocity of the y, but not the initial. That's a constant. What about its initial position? It's also a constant. What shape does this make in math class? What type of graph does this look like? It's a parabola. So if I plotted this, it's going to look something like this. Is this the trajectory? No. It's almost the trajectory. I want to go over this subtle point. Look at this. The trajectory is talking about the path that an object takes through space. It relates the x coordinate and the y coordinate. So it has to do with the path. It has to do with y as a function of x. Now, to be clear, we're so close to that if we go back to here. Look at this. Watch this equation right here. You agree that t is equal to v initial x. Wait, I flipped it, didn't I? All right. Should be x over v initial. Yep. Let's check the units really quick. This is actually the one I screw up the most for some reason. I always screw up this equation. So I get meters over meters per second. That's meters times seconds over meters seconds. Okay, so time can be rewritten as x over v initial. Well, what I'm going to do is do some work for you and just look at this equation. It's in the book. We can rewrite this as y. So I'm just going to take this equation, plug in this right here for time. And I can plug in a couple of other parameters, and what we get is y is equal to y initial plus x tangent theta. Remember, there's a sine here, there's a cosine there, you get sine over cosine. Anyways, that's where the tangent comes from. You get a v initial over a v initial that drops out. Remember, v initial y is not v initial. Minus, what is it? G, I don't want to screw this up. X squared. 2. I think it's that. I just want to confirm that I'm not screwing this up. Okay, now look at this. I just want to point out this is a constant. So is tangent theta. There's only one launch angle, right? This is the angle of the initial launch. And then look at this. G is a constant. The initial speed is a constant. The initial angle is a constant. Those are all constant. This is also a parabola, but this is a parabola that describes y in terms of x. This is the trajectory. See the subtle difference, if I could spell. You're gonna hear me say that word trajectory a few times towards the end of class today. That's why I want to make sure you understood that trajectory is the path in space. So far, so good? Yes, question.
What would be the other one though? Why with T?
This is just some parabola.
Just random
Yeah,
problem?
it's a parabola that describes the vertical coordinate. If I could,
It's like two-dimensional.
trajectory is in 2D. Think about it like this. Let's say I was watching this ball and I'm like some giant ogre, which is fairly true, and I could trace the position of the ball vertically without moving my finger, right? The ball would go up and then it would come back down, right? So you could think of the Y versus T as the shadow of the ball on the vertical axis. So that Y versus T plot is literally describing the motion of my finger up and down. Is that cool? Yeah, that's basically all it is. Which that actually relates to just throwing a ball straight up, because again, the X motion, as we saw, remember that launch earlier? We saw the ball launch horizontally, it didn't affect it compared to the vert. It's literally what would happen if I ignored the X component and just threw the ball up at this speed. Then it would just go like this, right? That's what that Y versus T plot is. It's what happens if you just ignore the X component. That describes the motion in time. Good? Yeah. Now, I'm assuming you've seen this before, done this before. Maybe I use a little bit different words. Just give me a thumbs up, thumbs down, how you're feeling on these terms. Was this an okay review? Okay, all right, good. What do you think here? Should we try a problem and then take a break? All right, let's try a problem. Now, I'm going to say one more thing. These are standard projectiles. This is the type of projectile problem I might like to put on your test. A lot of times in high school physics, you might be learning about level ground problems. To be clear, I rarely use level ground problems on tests. Now, that said, if you look on the bottom of page 72, for level ground problems where the initial position and the final position have the same vertical coordinate, or basically as long as y initial equals y final, that's level ground. Only for those problems does the time to the top equal the time to the bottom. Look at this one. Right? It might take 1 second to reach the top and 2.5 seconds to get to the bottom. In this case, you can't just figure out the time to max height and double it to get the entire time of flight. That's like the common pet peeve I have. Students will be like, well, it worked for me in high school. That's probably because in high school, you might have used a level ground problem. So it's just want to make that clear. If you want to know the tricks for level ground, it's not bad. That's fine. All right. So the problems on page 73, what do you notice about all of those? What do they all have in common on page 73? They're all level ground. So we could start with those, but I might mention that maybe you could try them later at home because those should be the easier problems. And I've got solutions. So let's go to page 74. On page 74, I want to start with problem 4.13. Okay, so I'm going to start with 4.13, and I want to stress this one piece. You're going to make charts showing your knowns and unknowns, probably a lot like what we're showing here on the board. Hold on a sec. You're probably going to have charts like this. So when you do these problems, this is what I want you to do. If you have numbers to plug in here, by all means, write the numbers here. However, when you're doing the math, just trust me on this one thing. Move these symbols around first, and only when you get to the final answer, only then do you actually plug in the numbers. Get in the habit of moving the symbols around first and plugging in the numbers at the last possible moment. If you do this, all the problems will start to look the same. On test day, you're more likely to recognize the problems, you're more likely to succeed. All right, and it's faster in the long run. You may not like it at first, but in the long run, you'll be so much faster. Okay, go. I'm going to erase. Talk to your neighbor. Alan, you can circle while I'm, erasing and getting caught up. On Zoom, I'll be erasing going forward, so it's going to take me a bit. Talk as much as you want. Want to stand up, stay awake. That's cool. Do some jumping jacks so you don't freeze in this ice box of a room that we have. It's cold in here. Bring a jacket, glass, or a puppy or something. Just in case it gets cold sitting out there. You could keep circling out. I'm just getting a picture on the board. You know what I'm saying?
Yeah.
But at least I'm catching one of those things.
All right, I'm gonna do a couple of loops and then we'll talk about it. Checking with you on Zoom while I'm up here. Any questions from Zoom? Obviously, you've got the solutions. You could try to at least get the list of knowns and unknowns before you check the solution. So maybe if you're not sure, get the list of knowns and unknowns, check the solution, then keep proceeding. All right. So far, so good. Yeah, don't forget, you got the solutions up here if you need laptops or whatever.
Pretty good.
Okay. That's my deal. Okay, all right, all right. I think that's not. You're on the equation. What's that? Yeah. Go ahead and switch these to your equation. Usually there's three big equations to solve. Y equation.
No, what about the final thread? What would that be?
Remember, there's only one equation. X. So I write those down. I can do that stuff. Check what's going on.
Yeah, I think this is the first one I think. We have to show back to the time.
Do you agree we don't have one of this one? Do you agree that it's not the same speed? Yeah, so watch out for that. So here- Well, actually, wait, in part A, where are we going?
So there's no acceleration.
That's gonna help out a lot. See what I'm saying? Other than that, I think you're good. What do you think? Got some ideas? Yeah. Cool, cool. Yeah, good. You got your A, Y, and the X in there. Cool. All right, all right. What do you think? Doing all right here? Okay, okay. Well, lifting your, okay, got it. Okay. How about you? What do you think?
No, I know, but I'd just rather get like good at it. Job out there.
Geez, we can see how important units are with these two numbers. Because, right, you got it right. You did it correctly. But so, right, do you agree that 9.8 meters per second is different than 9.8 meters per second? Yeah, so it's cool. Nice. And you remember this. I'm trying to say good job. All right.
Oh, I see what you mean now.
Why is that? What's the final one?
Because we're supposed to be different with the max height.
Acceleration.
Nice. So there's enough, it's knowing zero. Okay. What's up, Linda?
I'm just bringing my stuff back.
Understood. How's it going up here? Good?
It's going good.
Okay, yeah.
Kind of used to using the explanation of that.
Sure. Okay, get your equations on there. I think you have properly identified the Y.
Yes, sir.
Yeah. Cool. You're on it. Yeah. Okay, so you're gonna get those equations up.
Alright, sounds good.
Make progress. Yeah. Cool. So here's the only thing I would say. I would have gone all the way down. You can do that on the next slide. But the idea is you want to solve the equation algebraically before you play the numbers. Here's one of the reasons why. Use coding that is another reason. If we want to check units, we can check units before having to plug in numbers. Here's a third reason. It will become faster because you actually end up writing less stuff per line. It's not if you punch stuff in calculus, you're going to keep 4, 6, 8, There's a letter, right? It's usually one letter in subscript. You don't have to keep.
Oh, that's where.
It just ends up being so much faster. So try to get in that habit. Okay, the next question. Yeah, can I don't know, if like for example, just like, so like here, we're looking at T, right? He solves for a T like this. I think you may have screwed up. Check the units. Check the units. See that we actually.
Oh, yeah.
Yeah, and so the advantage, this is what I was saying, it's like, you might not notice that, but if he got to this point before he plugs the numbers, he's checked squares. Like, oh, whoops, and then he fixes it, that way he doesn't have to redo all that math. That's one example. What's up, Brandon?
Look at how this,
Math, friend?
Yeah, do you know how to get it out of that?
Who is your mode?
No, that's an information.
Oh, yeah, I'm checking.
Ah,
But it's, there's usually like math.
I'm doing Y. Or, my final grade equals to-
You know, I have to look it up, but it's something, it's either mode or set up, I just don't remember what stuff.
or delta Y.
I don't think this one, I think this is one I must have taken.
So, when I find max height, max height is velocity 0. All the distance, or you figure out the distance.
So everybody, I'm gonna go ahead and just put my list of knowns and unknowns up here. If you want to contribute, that's cool. Let's start with the simple ones. We know we're accelerating downwards with magnitude G, right? So what's AX? What's AY? Negative G. Some of you may have written negative 9.8 meters per second squared. That's cool. Now, in this case, how would I get the initial X? And I'm gonna be lazy with the sig figs, but then in the end, there should be meters per second there, right? Do I know the final X? It should be the same. If AX equals 0, this should be the same. And again, sorry, I'm being a little bit lazy with the sig figs. That's due to the size of the board I have to work with on Zoom simultaneous, whatever. Okay, how about V initial Y? What's that going to be? 19.6 sine, because that's right here, right? The sine is the vertical component because that's opposite to 30 degrees. The cosine is the X because that's adjacent. So gato. Do I know V final Y?
0.
Why? At max height. Yeah, because something in the problem told us we're at max height. So you're supposed to know that piece of information. Do I know delta Y? No. Do I know delta X? No. Do I know T? No. So we see there's three things we don't know here. Which equation might be the most useful? Well, I'm going to write down, we've got our delta X equation. And then we've got delta Y equation. We've got the final Y equation. And we've got the final Y squared equation. These are the big three. Are there others? Yes. Do we need them all? Not necessarily, but sometimes they're convenient, but whatever. Now look, which one of these equations is going to get the job done? If I number them, there's equation 1, 2, 3, and 4. We're trying to learn about max height above the ground. Which equation can help us get there in one step? You said the third one. What will the third one help us figure out? We know this, we know this, we know this. Do you agree that gets us the time? You could take that time and plug it in here. We would in theory know this. You could get delta Y. Do you agree that something about delta Y should relate to the max height? In particular, if I sketch the trajectory, right? I need a volunteer who's willing to show me what delta Y means. Can somebody come up here and just point with their hands or show me like what delta Y is? Or you can just describe it in words. What's delta Y? What does that mean?
Versus minus initial height.
Okay. Somebody said delta Y is equal to Y final minus Y initial. I agree with that. Well, what is Y initial? Is it here? No, it's up here. So delta y is actually figuring out this stuff, agreed? So if you can figure out that, hopefully you could add 10 meters to it, and that would be the answer we're looking for, right? Said another way, do you agree that this is y final, the final height above the ground? And so basically, we're looking for y final, right? This is a common thing on a physics test where you know it has something to do with y, and maybe you solve for delta y, but you don't finish the problem because you forget. I said height above the ground. We're looking for y final. Look at this last equation. I know v final. I know v initial. I know ay. Why not just solve it this way? Then I don't need the time. See what I'm saying? If we know this is 0, this is some number, this is negative g, we've got it. I'm going to bring that over here. We always plug in the zeros. I'm going to solve this for delta y. This is what I mean by solve it algebraically before you plug any numbers. In this case, remember, this minus sign is not canceled by that square. It would be like positive 9 or positive 25 over here, some number. I think it's actually going to be about positive 100, not quite, but close to that. And then when you bring it over, it should be negative 100. So it's the negative outside of the square. Flipping this around, doing some algebra, delta y should equal negative v initial y quantity squared divided by 2a sub y. You can take a second to figure that out and make sure you feel good on it. Wait a minute, are we going to get a negative number for delta y? Why not? Exactly, and that's why you hear me harping on this all the time. I'm not trying to be annoying. I just know how frustrating it is to miss a single minus sign, and then you miss the whole problem because you miss a minus sign. You're like, oh, why didn't I just notice ay was negative? So this is negative v initial y quantity squared all over 2 times negative g. And this helps me, I see, aha, it is positive. Before I plug in the numbers, I could check the units to make sure I didn't flip something up. Because my pet peeve is like, man, I go through all this work and then I plug it in and it turns out, whoops, the answer's wrong. Why not check the units before you plug in the numbers to see if you got it right? Well, in this case, we get meters per second squared divided by meters per second squared, which goes to meters squared over second squared times second squared over meters. Meters are the correct units for delta y. You out of here, Linda?
Yeah, I'm this is all there here in my car.
That's right.
Yeah, unit analysis guy, unit analysis, always check. your units.
Always check your units.
I fixed the calculator.
Oh, sweet. Cool. I'm sure I'll manage to screw it up before the next time you use it.
Yeah.
Right? See you, Linda. All right. What do you think? You can move over if you need to, or move around if you can't see. But and you got the solutions too. All right. What do you think, everybody? Is this okay? I think this is a good time to take a break. If you're close to finishing this up and you want to finish it up real quick, you can do part A or whatever. We'll come back and we'll do some more examples afterwards. All right. So this was just the first one to get you running and get a feel for it. So 10-minute break here. I got 5:51 on this clock. Zoomers, are you guys able to learn anything out of this crap? What do you think? Are you able to learn a little bit or not?
The x. Yes, the x will be the same thing. Yeah, be like the.
Typical Zoom reaction. Oh, I see. There's a check. Yeah, you could, yeah, hopefully, or in general, are you able to read like the subscripts and see the symbols that I'm writing on the board okay and stuff like that? Right on, right on. Okay, cool, cool. Gotcha, gotcha. Yeah, sweet. I mean, that's why I wrote these solutions. So hopefully the combination of me scribbling on the board, having the solutions, hopefully it's just enough to keep you rolling, and it seems like it's working. So, all right. We had a rough start like last week, but now it seems to be kind of going 2 weeks ago. All right, taking that break. I'll leave it up while you're in case you're using this while we're on break. Yes, question.
So for the D part, it asks for the quarter.
So the question is, they have a student that's asking me a question about part D. I'm just saying it out loud so they can hear you on Zoom. He's asking about part D, which is asking about determine the XY coordinates of max height. Okay, what's your question?
So for the x-axis, I got 16.97, but the significant figures is 3. Should I bump that up to 17?
So you said you figured out that delta X was, what did you say it was?
16.97.
Yeah, so this is a good question. Generally speaking, what's your major?
Mechanical engineer.
You should bump it up to 4 sig figs. Typically what happens is we use 3 sig figs for all our numbers. However, if the first digit is a 1, we oftentimes write 4. And that has to do with, think about it like this. If you're off by 1 in the 10th place, right, that's very close to 1% error. Whereas if you're off by 1 in the 100th place, it's close to 0.1% error. So now, if you have numbers that start with 2, 3, or 4, like 800, right? If you're off by 1 out of 800, that's much less than 1% error. And so by doing an extra digit on any numbers that start with 1, most of the numbers are well under 1% error. Does that make sense?
Yeah, so like on the exemption, I just marked the line under the number 9.
Sure, you could do that. You could also, I mean, you could just, now look, on the exam day, I'm going to grade either as full credit. So you could say 17.0, full credit. You could say 16.97, full credit. You could say 16.97 underline meters, full credit. Now, in Dom's class, he hates that. What you can't do is do 16, what's the next digit? Do you know the next digit by chance? So you can't write this. That's not acceptable because 5 is too many. In my class, I would let you write that. In Dom's class, he would want to strangle you and say, don't do that. Jorstad's weird. Which is true. I am weird. Okay. So, but I'm willing to let that slide. I figure that's something you can kind of dial in your engineering classes. Is that good? Yeah. Let's take a look at something here. So I want to show you something real quick because I know we're getting tired. It's late. Sometimes it helps to see a simulation of something. And we can talk about this thing. So I've actually got a whole bunch of simulations lined up, and I thought this might be an exciting thing to do is look at some computer programs. Whatever. Give me a second. I'm going to share screen on Zoom. All right. And then I need, what is it? This one? This one. Whoops. Okay, what was our initial speed? It was about 20, right?
19.6.
Okay, I'm gonna round that to 20. Wasn't our angle 30 degrees? And okay, so this is supposed to be a simulation of our exact problem. And I'm just gonna point out the following, right? We've got 10-meter height. We've got this 30-degree angle, 20 meters per second. That's approximately 19.6. And notice right here, air resistance is turned off right now. Okay, so what I want to do is first, I'm just going to clear those annotations and run it. We see the ball goes up, hits max height, and it's coming down, and it's taking forever. So let's speed it up. All right, let's run that again. That's normal speed here on this simulation. Now what I want to do is I want to show the velocity vector and run this again. So I'm showing the velocity vector. This time I'm going to run it slow. What do you notice about the velocity vector and the trajectory at any point? What do you notice about the velocity arrow relative to the trajectory? If you said it, I couldn't hear you. If you were doing calculus class, what would you notice about that velocity relative to the curve? It's tangent to the curve. So notice the velocity is the slope of the trajectory. It's not the slope of the YT plot. Do you agree? It's subtle. But just remember that. Keep that in mind because this is going to come up again and again and again. Velocity is parallel to the path you're traveling. Now, if I split this into components instead, and I want to label this really quick. Right here, this is velocity in the y direction at some random instance. This is velocity in the x direction. Let's focus on the length of the Vx arrow, right? Focus on this length right here throughout time. Okay, let's run this again here. Ooh. Oh, let's just have, oh, it won't let me do any more. Sorry, I was having fun. But do you notice that the Vx isn't changing size? I'll run that again. Look at the Vx arrow. It's not changing. Vy goes to 0 at max height. So this time we'll focus on Vy. And we'll step it. So just to be clear, we're looking at Vy. Notice over here, Vy is greater than 0. It's positive. We keep going. Step it. Right at max height, right about right there, what's Vy? 0. This is what we were assuming. So velocity is not 0 though. Do you agree that the velocity is still v initial x? So velocity at max height as a vector, I know I'm just stressing this, is equal to v initial x in the I hat. What's that?
No, there's just something in my eye.
Oh, okay, my bad. Okay, so then let's keep rolling. And notice over here, Vx is negative, agreed? Or sorry, Vy is negative. So far, so good? All right. And then I'll show the acceleration vector too. Let's just run this again. Notice the acceleration vector is that arrow that's always pointing straight down. And because it's pointing straight down, it has no x component. It is independent, right? The y component is independent. It is not affecting the x coordinate. So far, so good? All right. Just for fun, let's clear all this. If we put on air resistance now, we could see what should happen. What do you think will happen to the impact and to the time of flight? Kind of discuss with your neighbor. If we add in air resistance, what do you think should happen? Right now, the time of flight is 2.77. The range is 48. We add air resistance. You can look at the height, right? The max height was about 15 here. Remember, this is not exactly the same as your problem because we had 20 instead of 19.6, but here we go. Let's run it. Notice there's an arrow pointing to the left. There's an acceleration to the left. Dramatically less range. Which one was in the air longer? Was it no air resistance or air resistance? But it's pretty close. Do you agree? Sometimes air resistance can actually, right? Think about this. If you use a parachute, it will take a lot longer to fall than if you have no parachute. So sometimes air resistance can actually make it take longer to fall. Depends on the problem, right? Okay, anyways. So far, so good? Yes, question.
There is a spin on the ball. Would it help?
The Magnus effect. Yeah, have you seen these bozos that throw basketballs off giant dams? It's super cool, right? That's chapter 14. We could do that in here and we'll do some weird Magnus effect. Yeah. I mean, that's a really cool video. I love it. Yeah. Yes. For sure. So spinning makes, yeah, so we're ignoring so many aspects of physics at this point. We're ignoring spin, air resistance, yeah, all that stuff. All right. Any other questions? I have one. Well, this is all with AX equals 0. What would it look like if there was some AX, right? Let's look at this one. In this case, we see two arrows. Hopefully I'm still screen sharing, right? Thanks. Okay, so in this case, which one of these arrows is the velocity arrow? Is it the large blue arrow or is it the smaller red arrow? What do you think? Which one follows the trajectory? That is the velocity vector. Notice which way the acceleration vector points. In the direction of the concavity of the curve. Do you see that? The acceleration points in the direction that it is concave. This looks really complicated, doesn't it? I wish we could see this with components. Now, first I got to edit this program and read something really quick. Okay. Just in case I don't have the same parameters here. Aha, they were slightly different. Did you see that? Okay, so now I'm going to run this one. This is with the components. So notice it's the same exact simulation. In this case, the light blue arrows are indicating the velocity. So notice in this case, it's not going straight up, but it's pretty darn close to straight up. Do you agree? So we see that the velocity in the y direction is large and positive, and v sub x, it's not 0, but it's pretty darn close to 0 right at this point. You agree? It's not moving much left and right. And notice here, it's kind of hard to see, but here I could see ax is non-zero, and ay is so, it's smaller than this, so it's covered up. Ay is greater than 0. AX is 0. Sorry, that's sloppy. So far, so good. Let's look at this in the code and see what it looks like. Oops. Okay, I know this seems crazy. Can you read this or is it too small? You see it in the back? How about back there? Good. All right, now look at this. These are the constants. The initial position, the initial velocity, and the acceleration vector are constants. We're doing a constant acceleration problem. Okay, boring, boring, boring. You draw a ball, fine. We're going to set the ball's velocity to the initial velocity, the ball's acceleration vector to the acceleration vector. Boring, boring. This is just so you can make it wait for the mouse click. Boring, boring, boring. Look at this. This just tells it how many frames to display. We're only doing 5 seconds. Let's get into here. This is all right through here. This is the guts of the code. Look at this. You take the ball's velocity and add to it a dt, right? This is the equation delta v over delta t equals a. All right? That's all that is. This one right here, similarly, this is, oh, and I think I lost a vector there. This is delta x over delta t equals v. And I know you're probably a little tired and bored of looking at code, but I want to emphasize one more thing here, all right? This is going to be the same in pretty much every code we write. If you're trying to animate something, you just split this up into small steps and we animate it. So far, so good? Let's look at another one. Look at this one. In this case, look, the acceleration is changing wildly and it's doing something weird, right? Hang with me. You have an initial velocity and an initial acceleration. Now in the loop, look, you still have the same crap we had before. You just add one line. First, you compute the ball's acceleration, and then it's the same crap. This is like 3 lines of code to do this. Why are we doing this? In this problem, you could imagine this is the moon orbiting the Earth. And we could analyze this motion in 3D, right? What's the code got to look like? You have some rocks, we have a force. So it's the same, this is basically the same two lines as before, but what do we do first? We calculate the force, then we use the force, momentum, velocity, same thing. We update the velocity, then we update the position. And it's seriously, this is just a bunch of words and arrows and colors and graphs. We don't need all that. It's 6 lines of code. This is the same. Now I'm trying to show you this for this reason. A lot of students, when they start coding, are scared of it. If you put the time in, it turns out a lot of problems are easier to code. Think about this. You try and figure out this trajectory on paper and pencil. Let me know when you're done. I'll be dead. Okay? Seriously, it's going to take you so much time to figure out this stuff on paper and pencil. We need to learn how to use codes to be modern scientists. That's just the way it is. And I apologize if you don't like it, but that's just the way things are going. Paper and pencil calculations are great for checking your codes, but you need to learn how to code, and that's trying to motivate you. All right, any questions on that? You look so excited. All right, yeah, so hopefully that was, this was again, just trying to motivate why you should care. Now look, I see the time as 6:20. I'm gonna stop this share. Right, all right, so my claim is at this point, you need to practice. This is actually where we ended in the earlier lecture. I could rush on, but then I'll have to redo, I'll be off schedule. So what I think we should do is just spend the next 15 minutes doing a problem and then get the hell out of here. Let's do another problem, and here's what I recommend. Okay, here's the problem. Let me get the lights on and turn this off. Sorry if that was too much. All right. I'm trying to motivate you. I remember I hated coding. This Python stuff is so much easier than C. Right? Remember having to code C or Turtle, Pascal, or Fortran 90 back when I was a kid. Started in BASIC, and I was coding. I had to record my programs on audio cassette instead of diskette. Old technology. Punch cards. We still had some in the lab back when I was a kid. All right. All right. So here's some problems that you could do. All right. If you're still learning and still kind of bad at this, 414 is probably the easiest. Right. It's a continuation of the problem we just did, and it talks about the impact angle, and you can see how that's different. All right. If you do 4.18 or 19, AX is not equal to 0. These are called non-standard problems, right? So if you're curious about non-standard projectiles, you could do one of those. And then 420 is a good problem. So is 421. I'll say getting towards nasty, getting nasty. They start to get a little bit nasty there. And if you care, 15 and 16, like if you're just beat, oh, 17 is a sneaky one. 17. How would I say this? It's sneaky. Oh, yeah, I like, oh, yeah. So this is like, these ones are kind of like test level in here, all right? Similarly, if you want conceptual, if you're just not wanting to do a lot of math, 414 and 415 are conceptual. So if you just really want to hammer the concepts, you can hit those. I think that's plenty to choose from. So if you wanted to get cracking at these, let's take a look at these. Let's work for about 15 minutes. And since we're just working, I might go ahead and stop the live stream here. That way I don't have a bunch of boring nothingness. I'll still keep Zoom open, but I'm just going to stop the live stream. You know.